Hi guys! Today's topic is my purchase of an inexpensive logic analyzer. But what is a logic analyzer anyway? Well, in the electronics world, there are many different digital interfaces for data exchange between the individual components such as ICs, displays, buttons, etc. Commonly used protocols include I2C, SPI, CAN, LIN, and one-wire. If you develop, analyze, or repair a circuit that uses these protocols, it would be a great advantage for troubleshooting. For example, to see which data is actually being transmitted on the interface. Here you can see the display of my oscilloscope with an I2C data packet. My oscilloscope does not have a built-in logic analyzer, and the memory depth of 1,200 memory points is too low to examine a data transfer from several packets in one capture. However, a simple logic analyzer can be used to analyze this data with a lot of memory depth. I decided on a clone of a simple Saleh logic analyzer. This is apparently very common and is supported by several programs. I find this offer very attractive here on Aliexpress. The maximum clock frequency is 24 MHz and it has 8 channels. That is more than enough for most applications. The module has a housing, the USB cable is included, and signal measuring cables are also included in the delivery. I will order this one. I will often want to measure directly on the connections of an IC. I want to see if I can find suitable measuring cables with mini terminal connections. I like these ones. The terminals are so small that you can connect them to the connections of a standard wired IC. I will order them too. I will list the product links for you in the video description.
1 week later.
The assignment of the terminals to the colors of the cables was clearly not done by an electrical engineer, but that shouldn't bother me at this price. The cables are connected to the analyzer using this socket. It works, but it's a bit wobbly. I will therefore quickly mount a suitable connector on the cable of the mini terminals. Then you can easily plug and unplug the cable. There, done! Now let's test the analyzer. PC software is required for operation. SIGROC has an open source software called PulseView. It also works with this analyzer. When you connect the analyzer to the PC for the first time, nothing happens at first. You first have to use the Zadig software to change the driver from unknown to WinUSB. This takes a moment, but the driver is installed in the background. You can now start the PulseView program. This is the program window. The logic analyzer has already been automatically recognized. When I click on Run, the analysis of all channels apparently starts immediately. But no signal is connected yet. There you can select the number of samples to be acquired. If I select 1K, an example 1000 samples, the program automatically stops the acquisition after 1000 acquisition points. The higher the acquisition frequency is set, the shorter the possible acquisition time. That is logical because the memory can only store a certain number of points. The acquisition window can be moved by holding down the left mouse button, and the display can be enlarged or reduced using the mouse wheel. If you don't have a data signal to hand, you can simply activate a demo mode here instead of the connected analyzer. If you start the acquisition here, various demo signals are generated. I will stop the recording again right away. If you now zoom in on the display with the mouse wheel, you can see the many details of the signals. But let's get back to the real logic analyzer. This is what it looks like when a real data telegram is recorded. By the way, by clicking on the channel symbol to the left of the signal display, you can change the name of the channel, change the height of the signal bar, and set a trigger type. That works quite well. But it is important that you select a sufficiently high sampling rate. This should be at least 3 times higher than the highest pulse frequency of the protocol. This is the only way to ensure that the exact values are correct. This data telegram comes from a data transfer with the DS18S20 temperature sensor according to the one-wire protocol. But you can't do much with a display like this, unless you are able to decode it in your head. Wouldn't it be much nicer if the program analyzed the contents straight away and displayed them as text? That's exactly what PulseView can do. In the decoder selector menu, which can be activated using the orange-green data symbol, you can activate various decoders. Unfortunately, there is no decoder for the DS18S20 sensor in the selection. But since the software is open source, you can easily add external decoders. I found a software decoder that uses the same basic commands as my DS18S20 sensor. After downloading, you simply have to insert to the decoder directory into the decoders folder in the standard program directory. After restarting the program, I can open the decoder selection. Under sensor, we find the entry DS28EA00. By double-clicking on it, I add the decoder to my acquisition window. A corresponding symbol appears on the left side of the window. By clicking on it, we can select the entry for the channel used on the logic analyzer under OWR in the drop-down menu. In this case, it is channel number 4. We don't need to set anything else here. By clicking outside of this window, we close this selection. By the way, if you want to remove a decoder from the logic window, all you have to do is right-click on the decoder symbol and click on Delete. If I now start the measurement by clicking on Run, the measurement runs for the period X. In the circuit to be examined, the digital temperature sensor is only queried approximately every 10 seconds. Therefore, the sampling interval must be correspondingly longer. This channel is connected to the data pin of the DS18S20 sensor. If I now place the mouse pointer over a data packet and turn the mouse wheel upwards, the affected area increases. As we can see, the signals are wonderfully recognizable. The decoder also displays the correct decoded data. The hexadecimal command 44 hex is sent here. This starts the temperature conversion in the component. In the other data packet, the sensor sends the temperature as 2 complements with sign. This data packet contains the temperature plus 19 degrees Celsius. If I reduce the sampling rate to 25 kHz, which corresponds to a sampling interval of 40 microseconds, and sample the data signal of the DS18S20, you can see that the decoder cannot analyze the data properly. Pulse duration in this measurement is 15 microseconds. A good sampling interval would be 5 microseconds. This corresponds to a sampling rate of 200 kHz. This means that decoding works without any problems. What a useful tool! If you write a program and the digital communication is not working, you can use it to determine why it is not working. If you want to analyze a device, you can use the logic analyzer to listen to the data connection, e.g. between ICs, and decode it in order to understand the function. Many components, such as ST7735 graphic displays, ADXL345 sensors, and the RFM12 radio module, are also supported by their specific commands. If you have a defective digital device, you can narrow down the error much more quickly by analyzing the IC communication. I am definitely happy to now own this inexpensive logic analyzer. If you are not already a valued subscriber, you have now the chance to become one. If the video was useful for you or you found it entertaining, I would be happy to receive a small donation. You can find the PayPal donation address and information about this in the credits. Please click on the thumbs up and write me a nice comment. The algorithm likes that and it helps the channel. Also take a look on my product recommendations in the video description. It's worth it. After that, it's also lucrative to take a look on my playlists with the different categories of my many interesting videos. I hope you have a great time. See you next time. Bye bye.